So this is a work in collaboration with my colleagues from Bari. And I'll show you some applications of quasi-interpolation to unsupervised clustering techniques. So I decided to divide my talk in two parts. The first part is related to time series and quasi-interpolation. And then we see, if I have time, I'll also go through quickly the second part. And the second part is about copulas, probability densities, and spline quasi-interpolation. Okay, so we heard already a lot about time series, I think, in the talks from Wednesday. So I will go fast. I just need to revise a bit the notation I'm using. So we have a collection of observations that we call realizations. So you have some data collected at a certain time instant, and you are assuming somehow that underneath there is a smooth model denoted by F. And then you usually also think of some noise. So we are going to try to approximate this underneath model by using spline quasi-interpolation. And this is important because it allows you to somehow perform some analysis on the time series. So kind of try to infer some knowledge from the data that you have. Okay, already this we heard a lot. If you have noisy data, it's never a good idea to go with some global methods like interpolation. And it's better to try to construct some local approximation, for example, by using quasi-interpolation. Quasi-interpolation is very efficient under computational point of view. It can produce a smooth model, and then you can avoid some nasty things like overfitting. Okay, this is the very general form of quasi-interpolant spline. You have a B-spline basis, and then you have some coefficients, some functional. This was beautifully explained by Carla and also Hendrik, so I won't go into details here, but as you change the coefficients or the way you compute them, you may derive a new quasi-interpolant. So for this, for this application, we used a spline quasi-interpolant operator that was introduced by Mazzia and Sestini in 2009. And this is a type of quasi-interpolant operator called of Hermit type, which means that you need function values and also first derivative values to compute these unknown coefficients. So in our case, since we only have a discrete realization, we are going to use a variant of this scheme that was still introduced by Mazzia Sestini later on. And the variant scheme, you don't need exact derivative, but you can approximate this derivative you need by using some finite difference scheme. So in our setting, let's say we are going to use for this application the degree 2. And in this case, even if you're using the variance scheme, let's say you can pre-compute those coefficients, so you don't need to solve a linear system every time. And this becomes very efficient. Okay, so as I mentioned at the beginning, we have some noisy realization. The very first thing you can do, which is very easy, is to apply what is called a moving average technique. Just to put it simple, it means that you're going to choose a window of a certain length, a sliding window, and in the simplest case, you can somehow replace every realization with some average values of the realization falling within this window. We did a slightly more advanced things, like rather than using the average, we are going to use a local least squares approximation. This is just to remove a bit of noise from those realizations. And the degree here, you can choose whatever you like. Can be a linear, can be quadratic. You shouldn't go too high with the degree because these are noisy data. So after you do this, let's say you have now kind of clean data. And so what we are going to do then is to approximate the first derivative values and also the second derivative values with finite difference schemes. And then what we are going to do is to express the final underneath smooth model by using a spline integral representation. And here you have, let's say, this formula here. Okay, so just up to now to see what we did, and this is just some visual inspection. So let's say you have some noisy data. These are artificially generated. They simulate some random walk process. So what we are going to do here, okay, just try to see if we can produce some smooth model underneath. So this means Hermit, QI, integral, and least squares, because there is this small regularization at the beginning. Okay, so just to see what we are producing now. So now we are going to use this to perform some analysis on the time series that we are going to use. And specifically, we would like to check for anomalies. So to perform what is called anomaly detection, which means we are going to identify those observations that deviate from standard behavior. And what we are going to do is use unsupervised learning technique. Specifically, we are going to employ some standard clustering methods. These are some 3 very common clustering techniques: DB-scan, LOF, and isolation forest. Okay, just very quickly to understand what they are for the people not expert in this topic. So DB-scan, this is an acronym for a very long name, which stands for density-based clustering technique. So what is density? This is not easy to define. So somehow it clusters, which means you try to identify some structures in your data. So to group them, to identify some groups, looking for densities. You have a point and then you look in the neighborhood of this point. So if you have many points in this neighborhood, it means you have a high density region. Then how you measure this neighborhood? Well, it depends also on a measure of distance and many other, let's say, technical details. What is good about this algorithm is that you don't need to specify a priori the number of clusters. And this shape of the cluster can be any shape. So you see here, it doesn't matter, but it's useful in this context because it doesn't force all the points to necessarily belong to certain partition. So let's say the points on areas where you don't have a high density, they are kind of isolated and can be thought as anomalies. And this is a very common clustering algorithm. The second one is LOF. LOF is a local outlier factor. It's very similar to some extent to what I just explained in the DB-scan. It's just that you have a different way to measure what is this neighborhood region. So you introduce a kind of local distance to understand what falls within the neighborhood. And then you have, the last one is a very much different approach. I don't know how much you can read, but so this is IF's isolation forest. So basically you randomly select a feature, and then you randomly select a splitting, let's say between the maximum value and the minimum value of this feature. And then you're going to iterate this splitting until you somehow can isolate these points from all the others. And so since, let's say, this recursive partitioning can be modeled as a tree structure, so let's say the length from the root node to the terminal node can be thought as an average of probability score, and this tells you what is an outlier, so an anomaly, and what is not, which means that the anomalies are thought to be those points that have a shorter path length in average respect to the other points. But these are all common algorithms, so we are using this common algorithm. Okay, so this is just an example that I'm showing you. Here are some data free available from Yahoo, and we are going to measure what we did if let's say the accuracy is correct by using these three common indicators. One is the recall, so ability to correctly identify all the anomalous samples. Overall accuracy, fraction of correct prediction over the total number of samples, and the ROC IUC, computed area below the perfect classifier by randomly varying a specific threshold. I want to specify that we know in this data set what should be an anomaly and what is normal, but we are not going to use this to perform our analysis. This is done just to check if what we did is correct or not. So here are the results just by using these common clustering techniques. So let's say that we put everything between 0 and 1. So 1 is the best result, 0 is the worst result. And in blue, here I highlighted the best somehow scores. But so if you are a bit into this community, you should know that this table is actually is not a good result overall. This is because, let's say, the accuracy that you reach shouldn't vary too much according to the indicator that you're using. It's not possible that you get a good performance by using recall, a very poor performance using overall accuracy. More or less, those metrics should all be varying in the same small range. So by using the standard techniques, let's say, this is not enough. So what we did, now we are going to use our quasi-interpolation with the initial denoising strategy to approximate the time series. So maybe here the pictures don't do justice, but so let's say you have this purple is the approximate spline representation. This red cross is the location of the true anomalies. And so look at what we did now. So what we are going to do is produce like a change of coordinates. So we are going to use a different representation. So we are going to use a new system, new axis system. You have on the horizontal axis the sign difference between the realization that was given to you into your data set and the spline model at the same time instant. And then on the vertical axis, we write the first derivative of the spline model, still at the same time instant. So this is just the result I get, for example, with the initial QI and then this change of coordinates and then the loss. But probably it's better to look at this. So wherever you see QI, HI, and then the name of the acronym of the clustering, it means that we did this change of coordinates. So now you see somehow we these are way better results because all somehow these metrics agree and with what could be considered, let's say, true anomaly and what we could identify. We have already published this result. So me, Professor Mazzia and Dr. Tamburino, and this is everything is into this paper in 2022. And I also want to say that, so this was just a very simple example. Here there are more examples and then more advanced, let's say, methodologies to produce clustering. But already, let's say, at this level, we were very satisfied. So because usually you just use some common technique because they perform well and you are happy with the result. The problem is that if you use more indicators, sometimes the results that you get, they do not agree. And this is not a good sign that you somehow reach a good accuracy. Please.
Yeah, I usually measure this accuracy by using this so-called Jacobi index or ROU.
Yeah, this is true. So in this case, but not, I did it, but not for the anomaly. So this is just for anomaly detection, okay? What you're saying is more for clustering, okay? Mm-hmm. Okay. So this was, let's say, the first part. Okay, so since I have still plenty of time, I'll go through also the second part, but very quickly, because we already heard a lot, thankfully, let's say, about the theoretical background on densities and copulas. So I will just go through my notation. Let's say we have some random variables, and here the goal is to estimate the probability density function in order to determine the underlying probability distribution of a set of observed data. So we are going to call big F the cumulative distribution, small f the probability density function. What is the relation? Well, the density is the derivative of the cumulative. So what we are going to do is construct an approximation of the density by using the Spline QuasiInterpolant operator I just told you. And then after you have this, you can do again an integral representation to get the cumulative distribution function. But so bear in mind, this is the density, and so this is the derivative of the cumulative. Okay, so what we are going to do first, of course, we just have, let's say, discrete values. So the first step you can do, for example, is construct a discrete approximation of the cumulative by using the empirical cumulative distribution function. So this is a well-known formula, and you just apply it. Then what we are going to do, well, we need to know these density values and its first derivative values if we want to construct the Hermite type quasi-interpolant operator I told you before. Okay, so again, you can use some finite difference scheme to approximate such derivatives. This is not a big deal, but the most important thing is that what you constructed should be a density, because it should have a probability meaning, probabilistic meaning, sorry. So this is the expression that we have by using the quasi-interpolant operator. And to show that this is a density, you should show these three, let's say, requirements. Now, I'm not going into details because it's not difficult, the proof, but it really depends how you construct those coefficients. And in our case, it can be easily shown that with the construction that we have, this is actually a density. And so, of course, you should also show that what you construct is a uniform and consistent estimator. And this, again, I'm not going into details, but can be easily shown because you decompose somehow this error by using the so-called variance and bias formulation. And this, you can do this, let's say, to show point-wise consistency. Then, of course, you should show that this holds for every point. So you just put an integral and you get the same estimate. And then what's the end of the story? So now that we have a density and we have a cumulative distribution function, what we can do, well, now we can construct copulas. We heard about this yesterday morning. So again, I'm not going too much into the theoretical details. So, but what is fundamentals in copulas is this Sklar's theorem. It just says you that if you have marginals, you can easily construct the copula function, and then you can also go in the other way around. But the fundamental requirement is that somehow those marginals should be continuous. So then you know that the copula you're constructing is unique. And so now what we are going to do, well, we have a tool to construct this F1, F2, FD, whatever you need continuously with the quasi-interpolation. And this is what we are going to do. So we are going to use the quasi-interpolation operator to approximate marginals and then to construct copulas. But why do we need copulas to make clustering? Well, you can make a mixture of copulas, which means you're going to choose from some common families of copulas, and there are plenty of copulas. We chose from elliptical family the Gaussian copulas, and from the Archimedean families, the Clayton, the Gamble, and the Frank copula. And you're going to mix them by using what is called a mixing probability pi. So you are given a set of observations, and then you need to cluster this observation. How much this observation is coming from this copula, this is measured by a probability mixture. And this goes through, obviously, an optimization algorithm. Okay, so here I just show you a few examples. These are some synthetic data sets. You have strange shapes of clusters, four clusters. Here's the comparison with also other common clustering algorithms. So GMM stands for Gaussian mixture model. NK means is one of the most basic algorithms you can run. Don't look at the colors because we don't do this in a supervised way. So you cannot get at the end the exact same labels, but you should look if the partitions are correct. So for example, all these points here should belong to the same cone. And if you look at this GMM, for example, here you see 3 clusters. So it means this is not correct. Or the k-means, here you see 2 clusters. This is not correct either. And this is the one we are using. And so you see, it was able to correctly cluster the points. What is also important is that with this clustering algorithm, you also have interpretability of the results, because you know exactly somehow what is the probabilistic meaning behind every structure. Because you can measure with this mixing probability how much these points come from the Gaussian copula, how much of this comes from the Gumbel copula, and so on. So it's not just exactness in the partitioning, but it also gives you some interpretation. So here I have some common metrics. Not going through all of this to explain because I would need probably an hour, but let's just say that you have involved the best result for this example. And so again, wherever you see this B as HQI, it means that this is our technique. And yes, so in this case, we somehow outperformed all the other methods. Here are some 3D data, but just 2 clusters. These are also synthetic data. Yes, and then yeah, I also have some real data set. This is called the Breast Cancer Wisconsin data set. It consists of digitized images of fine needle aspirates from breast masses. And you have just, let's say, 2 clusters, benign and malignant diagnosis. Here probably you cannot see much, but so what I did is the misclassification rate, because we know what should be a malignant diagnosis and what should be a benign diagnosis. The misclassification rate just means the percentage of, let's say, the images you wrongly classified. But we are running this in unsupervised fashion. All of these comparisons are correct because here just 14%, 10%, 12% of misclassification rate. But especially in the medical domain, I mean, you shouldn't be satisfied. You should always try to make a very low misclassification rate, because this is very, let's say, important. And so even if it seems trivial, numerically speaking, it's very much important. So we reached 8% or 9%, let's say, of misclassification rate, and this was somehow the best result among these comparisons. Here is another data set. So the 20 News Group is a very famous toy data set for text mining analysis. Here we select a subgroup of documents talking about technology, religion, and sport. So you have 3 clusters. And of course, when you have textual data, then you have to transform them into numerical data. This is done by doing some embedding in vectorial space. And this is very common frequency function, let's say. And so you have a term document matrix. This was the size of this one. So term document means you have, for example, on the columns, the documents, on the rows, the key keywords. Every element into this matrix, it's like it's a kind of frequency of occurrence of term I into document J. And so this was very big. It was pre-processed by a simple truncated SVD to 2 components, and then you run the clustering algorithm, and this is what you get. Okay, so again, this is our methodology. Here, maybe I can explain a bit this. So silhouette score just tells you how well defined is the cluster similarity. This Kalinski score this should be, let's say, the highest possible. And it's a measure of, let's say, how favorably you reach, let's say, a ratio of between cluster variance and within cluster variance. And then you have this Davis-Baldi score. This should be the lowest possible, and but you cannot go below 0. The Davis-Baldwin just tells you is a measure of compactness. So it just tells us how well separated the cluster are. And all these things are again already published in this paper from 2024, again with Mattia and Tamburino, my colleagues from Bari. Okay, so just to summarize everything, yes, so we use this quasi-interpolation with Spline to enhance some common clustering techniques, but also to derive some clustering, more advanced clustering technique based on copulas, because you can somehow approximate probability density functions, and this is very useful in the context of data analysis. Okay, so that's it. Thank you.